14.4 Solve trigonometric equations. Relationships are a lot like algebra. Have you ever looked at your x and wondered why? The first thing we need to talk about today is identity versus an equation. Identities were what we were doing in the last lesson, where we were doing, for example, sine squared plus cosine squared equals 1, and we said that that was true for all values of x. So that's the key point there. An identity is true for all values of x. It holds true no matter what x is, versus this, an equation, that holds true for a specific value of x. It's like when I say x plus 2 equals 5. That doesn't hold true for all values of x. That only holds true if x equals 3, right? If x equals 3, then x plus 2 equals 5. So an identity holds true for all values of x. An equation, on the other hand, is true for a specific value of x. And today we're going to be looking at solving the equations. Before I jump into this lesson, I just want to show something that we're going to be using. Since we want to be solving for all values of x here, if I ask you sine x equals 1, well, we've been doing it to this point and saying, well, where does sine equal 1? Where's the y coordinate equal to 1? That's right here, at pi over 2. That's true story. But think about when we were graphing y equals sine x. It looked like this, right? It was cyclical. When I ask you, where does sine x equal 1, that means where does it intersect the line y equals 1? Obviously, this happens here, but it also happens here, and it also happens here. It actually happens at pi over 2, and then this was 2 pi, so this was 5 pi over 2, and so forth. So what I'm trying to say is that, well, our answer happens at pi over 2, which is going like this much around the circle. But it also happens when I go around to there, and I go around another time. And so that blue one is my 5 pi over 2, because that's basically pi over 2 plus another 2 pi. They're coterminal, right? And then I could go around another 2 pi and another 2 pi. So this keeps going on. I have an infinite number of solutions to all these trig equations. So how do I write that? Well, I write this as x equals pi over 2 plus 2 pi k. Okay? Let me explain that. It's because I'm saying I go pi over 2, and then I can go pi over 2 plus 2 pi, or I could go pi over 2 plus 2 times 2 pi, which would be 2 1/4 times around, or I could go pi over 2 plus 2 pi times 3, because I can keep going around and around and around the circle. So this is really important. Let me just highlight a couple more examples. What if I had an answer like here, pi over 4, and also here, like 3 pi over 4. So I'm not talking specifically about the solution right now. I'm just saying, how would I write all solution sets that lie here and here? Well, we have pi over 4 plus 2 pi k, okay, because we want to do pi over 4, then we want to do 1 time around that lands over there, and then we want to do 2 times around that lands over there again, and 3 times around that lies there again. Remember, the 2 pi just means go around the circle once more, revolve once more around. Or over here, which is x equals 3 pi over 4 plus 2 pi k. Okay, good. What if, though, I gave you one that was here at pi over 4 and here, which is 5 pi over 4. Let's look at what's happening here. To get from here to here, I add pi, right? And then to get from here to here, I also add pi. So couldn't I just simplify this down and say, well, x equals, well, let's start at pi over 4, and then we could either add pi on, or we could add 2 pi on, which got us back here. Or we could add 3 pi on, which was landing there. So see, the little thing that I have is only plus pi k now. And I don't have to start at 2 different points. Here you'll see that if I tried to do the same logic, well, the here to here is obviously not the same width as here to here. So I couldn't just make it as simple as giving one answer. I need to separate it into two here. So anyway, this is going to be really important when doing our lesson today, is finding this general solution. When we go to solve 2 cosine x plus 1 equals 0, we do this like we've done all other problems. Subtract 1 first. 2 cosine x equals negative 1. Divide both sides by 2. Cosine x equals negative a half. That means where is the x coordinate? Negative 1/2. So look at your circle, and where is the x coordinate? Negative 1/2. Well, we have a triangle here, and we also have a triangle here. So we know this is 60 degrees, but I really need you to start thinking in radians. And so this is pi over 3 radians. This is also pi over 3 radians. So now we're thinking in thirds, so we know this is 3 pi over 3, making this right here 2 pi over 3, and making this right here 3 pi over 3 plus pi over 3 is 4 pi over 3. Okay, and so how can we simplify this down? Well, we don't have equal spacing here versus here. So all we can do in getting our general solution is x equals, let's start it at 2 pi over 3 first, plus 2 pi k, or then let's start it at 4 pi over 3, plus 2 pi k. Again, because I want to land here again, land here again, land here again. So that's what the 2 pi k is for. Now this one's a bit easier in that it's only asking you to solve on the interval from 0 to 2 pi. So only one revolution of the unit circle basically. So let's bring that tan over to the other side. All right, and then let's take the square root of both sides. But when you take the square root, remember you need the plus or minus. Don't forget about that in this unit. Okay, so let me break that into two different things. Tan x equals positive root 3 or tan x equals negative root 3. Where does that happen on our unit circle? Well, hopefully you know by now that the inverse tangent of root 3 is 60 degrees or pi over 3. If you don't know that, I just don't know what I'm going to do with you at this point. So where is the tangent positive? The tangent is positive here, right? Because remember, tangent's y over x, so positive, positive, or here, because negative over negative would also be a positive tangent. Okay, so 60 degrees, that would be pi over 3 right here. We're dealing with thirds, so why don't we just make this 3 pi over 3? So that means this is 4 pi over 3. Okay, so we have those answers. And then where do we have that the tangent is equal to negative root 3? Well, the tangent's negative here and here, and of course the reference angle is the same. It's that same pi over 3. So that would lead us to fall pi over 3 short, 2 pi over 3. And then this one, let's see, one whole time around would be 6 pi over 3. So fall pi over 3 short, that leaves us at 5 pi over 3. So this question's being really nice. They're just asking us for answers within 0 to 2 pi. So I don't even need to do that plus pi k thing because I only want one time around the answers. So x just equals all those things I circled. Pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. However, for the sake of practice, let's see if we can find any pattern here if this wasn't just a restricted domain, if I wanted it for all values of x. Let's see if we can find a pattern. How do we go from here to here? Pi over 3 to 2 pi over 3, we just added pi over 3. That was it, right? And then to go from here to here, what did we do? 2 pi over 3 to 4 pi over 3, oh, well, we added 2 pi over 3. So obviously, those aren't the same interval, so that's not going to work. Let me erase that and start over. What other pattern might I pick up? Well, let's see. To go from here to here, I went from pi over 3 to 4 pi over 3, so I added pi. And then to go back, I added pi. Okay, that's looking good. What about the green ones? To get from this green one to this green one, I added pi. To get from this green one to this green one, I added pi. So I think I can come up with my solution there. Let me start with the gray. I started at pi over 3. And to get to the next one, I added pi. To get to the next one, I added 2 pi. So I'm just going to say plus pi k. That's the gray one. And then the blue one, well, I start at 2 pi over 3. You always want to start at the smaller number. So x equals 2 pi over 3. And then I added pi k. So those are my answers. If I wanted just a general solution for the problem they're asking me, that's my answer. But this would be the general solution. We'll do a bunch more, but I need you to start getting comfortable with this. Now we're going to find another general solution. So 2 cosine cubed x minus cosine x equals 0. Yuck. Oh, but look, there's a cosine in common. Take it out. Cosine x, 2 cosine squared x minus 1, don't forget your minus 1, equals 0. So now since we have it equal to 0, we can set each of the factors equal to 0. I can't factor that down any further, so just set each of them equal to 0. Cosine x equals 0, or 2 cosine squared x minus 1 equals 0. 2 cosine squared x equals 1. Cosine squared x equals 1/2. Cosine x equals plus or minus root 1/2, which is plus or minus root 1 over root 2, which is plus or minus 1 over root 2. Still not looking familiar. What does 1 over root 2 equal to? Let's see, let's rationalize the denominator. Oh, root 2 over 2. That looks really familiar. Yay. Plus or minus root 2 over 2. So let's tackle this one first. That looks easier. So where does the cosine equal 0? The cosine equals 0. That's the x-coordinate equals 0. Where? Well, it equals 0 here and here. At pi over 2 and at 3 pi over 2. Okay, so where does this happen? Let's see. Well, the positive root 2 over 2 would be here, right? So here is where I would have cosine being root 2 over 2. We know this is just 45 degrees, so that's pi over 4. And down here would be, well, that's 8 pi over 4. So fall pi over 4 short, 7 pi over 4. Okay, that's my positive root 2 over 2, but my negative root 2 over 2, which is over there, would be here, which would be, remember this is 4 pi over 4. So fall pi over 4 short, or fall pi over 4 over. And those are our answers. Let's see if we can find a pattern going on. Let's see, to get from here to here, we go 2 pi over 4, which is just pi over 2. To go from here to here, we go 3, 4, 5, plus pi over 2 again. To go from here to here, we go 2 pi over 4. This is looking good. We get x equals, we can start it at pi over 4, and then we just add on pi over 2k. If k was 1, this is this answer. If k was 2, that's this answer. Think about it. What if k is 2? We get pi over 4 plus pi over 2 times 2, which is pi. Pi over 4 plus pi is 5 pi over 4. If k was 3, that would be this answer right here. And k equals 4 would be one whole time around, because k being 4 is plus 2 pi, which is all the way around the circle. So that's what this is all getting at. Let's see if we can figure out this one. To get from here to here, we just go plus pi. To get from here to here, we also add pi, giving us x equals, we started at pi over 2, and we just kept adding pi k from there. So here or there. That's our final answer. Lots of answers that we have for that one. All right, now let's solve it in an interval again. So we're thinking that's slightly easier, but don't be fooled. Don't be fooled for a moment. This is example 4 for a reason. I have no clue what to do. I have sines and cosines. I'm really not happy. So what I'm going to do first is isolate the sine on a side by itself and isolate the cosine on the other side. So let's scoot the cosine over to the right. Things are still not looking good. I still have sines and cosines. This is a huge trick. Never forget it when you're dealing with trig. You know that sine squared plus cosine squared equals 1. That was your Pythagorean identity. This is how you transition from having sines and cosines to getting only sines or only cosines. Let me show you how. Go ahead and square both sides. So square this side and square this side. I get sine squared x. To square a binomial, you must foil or fail. And I get 1 plus the outer and the inner is 2 of those cosine x's, and the last is just cosine squared of x. I just promised you that I was going to be able to get all sines and all cosines. It didn't magically happen. It didn't magically happen yet. It's about to, because look at this. We have the sine squared, and the reason I'm tackling sine squared is because, see, this side has more stuff going on. I have cosines and cosine squareds, whereas this side is just a sine squared. You can solve for sine squared in this. That's 1 minus cosine squared, isn't it? Sine squared is 1 minus cosine squared. And so replace your sine squared with the 1 minus cosine squared. So just replace it. You're allowed to do that because they're equivalent. And now I've transitioned everything into cosines. Now let me just show you the reason that I knew that I didn't want to just square from the get-go was if I squared this, I would have gotten sine squared minus 2 sine cosine plus cosine squared, which wouldn't have made me any happier than I was because now I have this sine cosine, which I don't know what to do with, okay? So really important hint is to isolate the sine stuff on one side and isolate the cosine stuff on the other side before you get started. So that's what I did in this one. Now I'm just going to subtract 1 from both sides, and I'll just add the cosine squared at the same time. And so I get 0 equals, that cancels out, 2 cosine x plus 2 cosine squared x. And now I realize that I could factor out that 2 cosine x that's in common in both of these. And 2 cosine x divided by 2 cosine x is 1. Don't forget about the 1. Plus, you have a cosine x left here. And so now we can say that 2 cosine x equals 0, or 1 plus cosine x equals 0, which means cosine x equals 0, or cosine x equals negative 1. Well, where does cosine x equal 0? We just did that in our last problem. It was here and it was here. We're only evaluating from 0 to 2 pi, so I'm just going to say it happens at pi over 2 and it happens at 3 pi over 2. And where does the other one happen? Where does cosine x equal negative 1? Well, that's where does the x coordinate equal negative 1, and that happens at pi. Now, the one thing that you must do in these problems, when you're squaring both sides, you must check for extraneous solutions. The reason you have to do that, well, I'll explain that in 1 second. Let me just show you what I mean. So let's go ahead and check them. So x equals pi over 2. So you just start with your original equation. So sine pi over 2 minus cosine pi over 2. Well, the sine of pi over 2, that's just right up here. So remember, that's the point 0, 1. And so the sine is a y, which is 1, minus the cosine is 0. That's 1. That works. I wanted 1. Now let x be equal to 3 pi over 2. So we have sine 3 pi over 2 minus cosine 3 pi over 2. Well, the sine of 3 pi over 2 was down here. That's 0, negative 1. So the sine of 3 pi over 2 is negative 1 minus 0, which is negative 1. That does not work. So the reason we got this extraneous solution was because, remember, our first step was to square both sides. Well, the problem is that negative 1 squared is positive 1, which is why we got this extraneous solution. So that's why when you're squaring both sides, you must go back and check for extraneous solutions. X equals pi was our last solution to check. So the sine of pi minus the cosine of pi. Well, this is the point, -1, 0. So we get 0 minus a -1, which is 0 plus 1, which is 1. So that one works. So our final answer is x equals pi over 2 and pi, because we had to throw this one out. It was extraneous.
And that's it for this lesson.
Bye.